Hey math fans, welcome to Precalc, and we are taking a look at geometric series today. So, as you may recall, if we have a geometric series, it looks something like the first term plus the first term times r plus the first term times r squared plus the first term times r cubed plus the first term times r to the n minus 1. And we can write this in sigma notation. We'd say as I goes from 0 to n minus 1, a times r to the I. So when I is 0, it's a times r to the 0, which is a, and then I indexes up to 1, so I equals 1. We have a times r to the 1. Okay, so that's this term. Then I goes up to 2. We have I to the r to the squared. Let me see if I can turn on my highlighted mouse. And then this would be the second, that would be the third term where I is 2, then when I is 3, and all the way up to n minus 1. Another way of writing the same exact series would be a plus a to the r plus ar squared plus ar cubed plus ar to the n minus 1. And you could say I goes from 1 to n r to the I minus 1. Okay, so when I equals 1, r to the 1 minus 1 is r to the 0. That gives us that term. So, two ways of writing the same thing for geometric series. And we looked at the sum of a geometric series. And the sum of a geometric series for I equals 0 to n minus 1 of a times r to the I, that's equal to, if you wanted to do this, instead of adding up each term, we have a shortcut, and it's the first term. Okay, so that's a times 1 minus r to the n all over 1 minus r. Okay, so that will give you the sum of a geometric series. And you can do that on your calculator as well. Well, today we're going to talk about an infinite geometric series. Right, and so an infinite geometric series might look like 1 plus a half plus a quarter plus an eighth plus a 16th plus, and just keep going on and on and on. And you might be curious as to whether or not that has a finite sum or an infinite sum. There are definitely an infinite number of terms, but as we think about it, as we add 1 plus a half plus a quarter plus an eighth, the sum actually gets bigger, but by a smaller and smaller amount. And so one of the things we ask is, does the series converge or diverge? If the series converges, it means that this sum gets closer and closer to a finite number. Okay. If the series diverges, it means that as we add more terms, it just gets bigger and bigger and bigger. An easy example of a geometric series that diverges would be something like 1 plus 2 plus 4 plus 8 plus 16. each time each term is twice as big, and you can see that as we add more terms, the sum just gets bigger and bigger and bigger. That diverges. So the question here is, does this converge? And we can actually use what we learned about the sum of a geometric series to take a look at what happens. We know that it's equal to a times 1 minus r to the n all over 1 minus r. Well, in the example above, we know that a, the first term, is equal to 1, and we also know that r is equal to 1/2. And I should say in both of these examples it's important that r is not equal to 1, because then we'd be dividing by 0, and that would not be good. So we could actually plug this in and see what happens. Well, if the first term is 1, and we have 1 minus r to the n, but this time there are an infinite number of series. So what happens when we take 1/2 to the n as n gets bigger and bigger and bigger? Well, if you take a number that's less than 1 and raise it to, right, this is n is approaching infinity, raise it to something that's huge, 1/2 to something really big gets tinier and tinier and tinier. So this term actually gets closer and closer to 0. And so we end up with 1 minus 1 all over 1 minus 1/2, which is 1/2, which leads us to the conclusion that this infinite series, this infinite number of terms, if we add them up, gives us 2. Okay? And we can generalize this actually. So if the absolute value of r is less than 1, then the sum of an infinite geometric series is given by, oops, let me change that, as I goes from 0 to infinity, a r to the I minus 1. This gets closer and closer to a times the quantity 1 minus r to the, I guess we should say n over here, sorry, r to the n all over 1 minus r. But remember when we took a look at what happened to r to the n? Well, when n gets really big, if r is less than 1, then this whole term goes to 0, and what we're left with is a over 1 minus r. And so that is the sum of an infinite geometric series. So maybe we should do an example or two. Alright, let's go check out the classwork. And if I take a look at 13, if we take a look at A, we have the geometric series where the first term is 6 and r looks like it's 1/3. So this could be written as n's going from 0 to infinity of the first term, 6, times r to the n minus 1. Okay, and that would be the same as 6 plus 2 plus 2/3 plus 2/9 plus on and on and on, which would, if we want to know what the sum is when we add that all up, that's the first term over 1 minus r. So 6 over 1 minus 1/3, 6/2, you need to invert and multiply, and you get 18/2, which is 9. Okay? Let's see if we can take any questions, comments, or concerns. Alright, well, I can't answer them anyhow, so let's take a look at maybe another problem. So if I take a look at 14, let's see. Okay, so if I look at 14a, I see that 10, and I have -1/2 to the I, so my first term is when I equals 0. So the first term is 10 times -1/2 to the 0, which is 10. So that's my first term. And I can see that R in this case is -1/2. So if I want to know what the sum of that geometric series is, A over 1 minus R, 10 over 1 minus -1/2. So that's 10 over 3/2, or 20/3. And if you wanted to, you could actually write out the first few terms of this, right? We'd get 10, then times -1/2 would be -5, then plus 5/2, then minus 5/4, then plus 5/8, and this would be getting closer and closer to 20/3. Okay. If you take a look at B, this one's interesting because I start with n equals 2. So my first term is when n equals 2. My first term is 3 times 1/5 squared, which is equal to 3 times 1/25, which equals 3/25. So that's my first term. R is equal to 1/5, and now you can use the equation A over 1 minus R, and I'll let you work on that. Alright, so that's about it for infinite geometric series, and we'll come back and take a look at present value in a little bit.